Okay, welcome to this next video for Chem 161. Some further contributions to Chapter 3, touching on quanta and the energy of photons. And we'll see how these ultimately relate to the electron in some later discussions on the structure of the atom. Okay, so we start with the idea of breaking down some classical physics that was done by a German scientist named Max Carl Ernst Ludwig Planck, and he was responsible for trying to improve the output of light from Edison type light bulbs, and he tried to develop a model for the incandescence for various materials, and ultimately decided that no matter what the source of material, that there was no material that could ever be truly continuous in the amount of energy released as radiant energy for light. And so instead, he proposed that objects emit electromagnetic radiation only in integral multiples of a tiny little elementary unit called a quantum. Okay, so that is to say that energy isn't coming in this continuous, infinitesimally small amount, but little steps of energy are irradiated and come from things like incandescent light bulbs. Okay, so to define this, we had and to better define the energy of a quantum material, we have an equation here. So these here in the equation, we'll write it as E, and I'm going to put a subscript to indicate that this is the energy of a photon, which is a quantum of energy. Okay, so a little packet of energy. And so the energy of the photon is characterized by Planck's constant times the speed of light. So Planck's constant times frequency. Let me correct that. Planck's constant times frequency, so h nu. And we recall that Planck's constant h is equal to 6.626 times 10 to the minus 34 joule seconds. And we know that in order for this equation to hold, that we must have the frequency here in units of joules. Units of per second, 1 over s, or hertz. So you can see here that the product of Planck's constant and frequency in 1 over the second would leave us only with the joules part to give us the energy of a photon. Okay, so this is the energy associated with a single packet of energy that is a quantum model for energy coming from objects, including an atom. Okay, so that is therefore to say that the units we expect here are going to be in capital J, joules, and we've seen Planck's constants, and now we know frequency, of course, over there. So let's take a look at an example, and we'll say in the example, what is the energy of light having a frequency of 5.25 times 10 to the power 14 hertz. Okay, so we're asked to solve for E. So the equation tells us that we can answer this question. So the energy of a photon of this light that has this frequency is equal to Planck's constant time frequency. So we're after this energy. That's our unknown. We'll list the knowns. So we have Planck's constant, 6.626 times 10 to the minus 34 joule seconds, a very small number, indicating that each photon is going to have a very small amount of energy. And the frequency here, and this better be in hertz or per second. And so thankfully it's provided to us in that way, 5.25 times 10 to the 14 per second. So we can use the equation, which simply tells us to multiply these things together. So 6.626 times 10 to the minus 34 joule seconds times 5.25 times 10 to the power 14 per second. And you can see here now that the seconds will cancel with the per second, and we'll answer in joules. Okay, so the answer here in joules is going to be 3.48 times 10 to the minus 19 joules. And let's just reemphasize that we have just solved the energy of a single photon of this light, that has this frequency. If we were interested in the energy of a dozen photons, we would multiply by 12. If we were interested in the energy of 1 mole of these photons, we could report that as well. So as a follow-up, we'll say 1 mole of these photons as a follow-up to show this. Okay? So that was part A, and here's part B. So for this, now that we have the energy of a single photon, well, the energy of 1 mole of photons, okay, all subscript there, is going to equal Avogadro's number times the energy of a single photon. Okay, so here it's going to be 6.022 times 10 to the 23 times, so that many photons is the number is the number that we're after. So this is joules. That many photons is the sum. And if we multiply by the energy of a photon, 3.48 times 10 to the minus 19, we knew that it was joules, and I'm going to list here joules per photon. That's how we interpret the above answer. So there are 3.48 times 10 to the minus 19 joules per photon, and if we multiply by 12 photons, that would be joules per dozen photons. If we multiply by the mole, this is joules for that many photons instead. Okay, so in this case, this number is now going to be much larger than this tiny little number that is 10 to the minus 19. And instead we'll have the product here. So 6.022 E23 times 3.48 E19 negative. And now we have 209,565.6 joules per mole of photons. Okay, so we can also write this if you want to include the per mole piece, which we have kind of touched on over here. So the energy per mole would be 209,565.6 joules per mole, essentially dividing the mole piece to both sides. And so this is a way to write the energy per mole, which is often done for examples like this. Okay, so with that, we can try one more example. So let's make some room for that. Okay. And our next example here will be, what is the energy of red light having a wavelength of 700 nanometers? Of red light having a wavelength of 700 nanometers. Okay, so it's going to be a combination of two equations in this case. We have the one from above, and we have previously seen that energy is also equal to we'll develop a new equation here using the previous equation, which is where nu is equal to speed of light divided by lambda. This came from an earlier idea touching on how the product of frequency and lambda is equal to the constant for the speed of light. So we can put these two together and substitute for frequency and develop our new equation, which is simply E equals h nu. Now putting this in place of nu, and we have E of a photon is equal to hc over lambda. Another popular form of this idea for the energy of a photon, but now combining information for the constant from the speed of light. Okay, so that'll be our new equation to apply. We have a couple things to do. Since this equation, again, we need to use lambda in meters. So we must use lambda in meters. We know the constant here is meters per second. And we have the other constant, which is Planck's constant in joule seconds. We can see here the importance of using lambda in meters. So our first strategy is going to be converting the 700 nanometers into meters is the first part of this problem. Thereafter, we can apply that new equation of ours. So let's start this. Okay, so 700 nanometers times, go into meters. In 1 meter, there are 1 times 10 to the 9 nanometers, so a billion nanometers. And this gives us 7.00 times 10 to the minus 7 meters. Our lambda is now ready for our equation. So the energy of a single photon is equal to hc over lambda. So this is going to be 6.626 times 10 to the minus 34 joule dot s times the speed of light, 2.998 times 10 to the 8 meters per second, all divided through by now our wavelength in meters, 7.00 times 10 to the minus 7 meters. And we can now look to see if units cancel appropriately. The meters in the numerator will cancel the meters down here. The per second will cancel the seconds, so we will end up simply with joules, which is what we expect for the energy value. Okay, so the energy of a single photon is going to be the product of those two constants divided by 7.00 times 10 to the minus 7. Okay, so on your calculator, this is 6.626 double E 34 negative times 2.998 E8 divided by 7.00 E7 negative, and we get 2.8378 times 10 to the minus 19 joules, which is the energy of a single photon. If we had to report to the correct number of sig figs, we would need more information, or if we were given just what we had on screen here, we would interpret 700 as 1 sig fig. But for sake of clarity, I'm going to put a period there to indicate that that final 0 is significant. So we'll go to 3 sig figs on this one, which is how we reflected the level of precision over here. So we'll answer to 3 sig figs, 2.84 times 10 to the minus 19 joules will be our final answer there. So this is the energy of a single photon of red light.